unfashionably late. If anybody comes in, just tell them that I told you the secret to saving lots of money on your projects on the first slide, and then they'll feel really bad. But they'll be on time next. All right, so who am I? I'm Matt Pollock. I'm a senior systems engineer at National Instruments. I work in our embedded systems group. Generally speaking, I get to play with the big fun toys. When you see anything that's got a compact radio on it, that goes on our keynote stage. You hear about our customer case studies. Odds are pretty good that somebody in the system engineering or the A specialist departments at National Instruments were involved somehow. Usually it comes to us when it's big, ridiculous, and difficult, which is my favorite kind. I've probably worked on, 50, 100 different embedded systems with our customers start to finish. And over that time, I've seen a lot of mistakes. Have you ever made a mistake? Nope, you're lying. Have you ever finished a project perfectly on time and perfectly on budget? A few. Were they big or were they small projects? Usually I find that if you manage to finish your project on time and on budget with the compact radio system, either you've done it a number of times before or you really sandbag that estimate. Possibly both if you've done it before. So the goal of the presentation is to help you figure out what to do with the different pieces of our embedded platform. It's not just a single VI that lives on your Windows PC that you can drop a couple of express VIs down, please don't do that, and a couple of local and global variables and say that you're done. Please don't do that. Instead, we get to deal with a PC, real-time controller, and an FPGA, figure out what has to go on which of these different targets, get the data in between them in an efficient way, and then hopefully test and validate that our system works the way that it was supposed to. We all put in lots of time for testing and debugging, right? Oh yeah, you should. So ideally, we're going to talk about how to get from this, ooh, fancy animation, to something that looks like this, instead of something that looks like that. Please don't write this code. Yes, I've seen this code. I've actually seen worse than this code, but I'm not allowed to put it up on the screen because of NDA. It's terrifying to me, some of the LabVIEW code I've seen that gets deployed out into industrial systems, critical systems. I know that I myself have had to take a couple of shortcuts when it gets to that crunch time of development cycle. We're going to talk about some ways to avoid the pain of those crunch times if we can. I know you're never going to eliminate it entirely, that's impossible, but at least know about this stuff up front so you can plan for it a little better. Horrible eye chart. Requirements. This is actually the biggest failing I see in customers building out good compact radio embedded systems. Not knowing what it is they want to build in the first place. How many of you have ever had a customer give you perfect requirements at the beginning of a project? What? Really? Once. And that's probably your favorite customer of all time. Yeah. It just doesn't happen. So at the very least, there's a couple of questions you should be asking your customers to help feel out, is your solution appropriate? And what level of risk are you looking at? And I try and list those out here. So what kind of data acquisition rates are we talking about? Is it over a kilohertz or not? Because that gates some decisions that we get to make later. How many channels? Do we need to get an expansion chassis or can we fit it in one box? What are the loop rates and latencies that we need? Are we running at 10 megahertz or are we running at 5 hertz? Does it have to respond within a very specific amount of time from a stimulus to an output? If so, that might determine whether something goes in the FPGA or not. Ask your customers these types of questions, and it can usually gate what you need to do about it. What kind of analysis do we need? Are we doing a simple greater than or less than? All right, that's easy. Are we doing detailed wavelet analysis on waveform data? Not so easy. Where's it going? Are we logging gigabytes an hour to disk? If so, the little flash drive on a compact radio is probably not the right idea, since those actually have a lifespan. It's a non-renewable resource, if you like. Are we needing to talk to a database, or need to push everything over to a UI that's going to display everything? And if you're interested in how to get a nice embedded UI working on your compact radio, come to Aaron's session after mine. So assuming that you took a look at what you actually needed to build from the perspective of the data in your system. What's coming in, where's it going, and at what rates? That's when we try and break down the system into some modular pieces, processes, loops. Each of these should be responsible for one part of the system. Acquisition and control, sure. Logging to disk, separate. Communicating out over the network, separate. Watchdog functionalities. Any of you ever use the watchdog features on our products? All right. Any of you ever figure out that cluster correctly the first time? No, nobody does. Nobody.
It's wrong in the CLAD.
What's that?
It was wrong in the CLAD.
Ooh. Yeah, if any of you ever took the Certified LabVIEW Embedded Developer exam, that was partially my fault. Sorry. We can talk about it afterwards. But one of the most common questions that we get in system engineering is, all right, I've got some logic that I want to put on my system. Where does it go? What types of chunks should I break my system into? This is my cheat sheet that I give to my customers. Things that go on the PC side. If you're doing offline processing analysis, by offline I mean it could happen next week, tomorrow, it doesn't matter. But usually large data, databases, queries, that's going to be on the PC side. Anything that requires a user interface in a remote location is going to be on the PC side. Again, if you use our higher-end compact video controllers, they do have an embedded UI feature, and on those you can actually do it locally. If we're talking anything to SQL, or if we're talking to OPC DA, that's going to be over on the PC side. On real time, if we're doing online analysis, and I use the term there as something that needs to happen repeatedly in the loop with response times in the order of hertz to kilohertz. Example, taking a waveform, doing some quick analysis to determine what's the major frequency component of that signal. If it's too high of a frequency, start applying some control logic. Something like that would be what we do on the RT side. If we need to hold data temporarily, maybe stage it locally before we send it over to a PC, that's fine. But we shouldn't be doing gigabytes of data on a compact radio. If you're going to do that, at least get some network-attached storage or get an external drive that's actually rated for that type of data. And our loop rates, if we're talking about 100 microseconds, millisecond timescales, that's appropriate over for the real-time side. If we're talking megahertz loop rates, that doesn't happen on our RT controllers. And if we need to talk out to Modbus, Serial, CAN, LIN, etc., that's going to be done over on the RT side. If you're working in the automotive industry, you're probably dealing with CAN all the time. Down over on the FPGA, that's where we're doing inline analysis. So basically analysis on a point-by-point basis instead of a waveform-by-waveform basis. If you need response times in the order of nanoseconds or single-digit microseconds, that's when we're down on the FPGA. Usually that's what determines what has to go where, is your data rates and the processor clock. And anything that touches safety or time-critical operation, if jitter is utterly unacceptable to your application, it has to go on the FPGA or on external hardwired circuitry. The example I usually like to give here is an emergency stop button should not go through a shared variable. That should be a hardware circuit that when you press it, it trips it. And yes, I've had customers make an emergency stop button go through a shared variable before it actually does anything. Please don't do that. And if we're talking about low-level digital interfaces like I2C or SPI, that's going to be down on the FPGA as well. And I've got a session later today at 4:30 talking about the reuse designs that the system engineering group puts out. If you're thinking of designing your own I2C or SPI logic on FPGA, please don't. We already did that. Download ours, use it, and get on with your life. And we've got a number of other libraries as well. And I'll just put that plug out there. Come to my session, I'll tell you. Have you seen something like this before? Like a clean breakdown of what goes where? Some nods, some no. I've asked that every time I do this presentation, and the overall nods has been going up over time, so that's good. We're getting that message out. All right, so scan engine. How many of you use scan engine today? Some, a little bit. All right. Why did you choose it? It's easy, yes. What would make you not be able to use this?
High speed.
High speed. What's high speed?
Faster than like a millisecond.
All right. All right.
Up to 10 milliseconds.
Yep. So scan engine is what we in system engineering refer to as easy mode. It's a pre-configured personality that goes down on the FPGA that can already handle single point I/O at relatively slow loop rates. Relatively slow meaning once we get to kilohertz or above, I start taking a very hard look at the requirements. The reason is the scan engine is a polling loop that runs on the CPU of the real-time target. It's over here constantly polling at whatever loop rate you specify the I/O. Those of you how many of you have put a while loop on an RT target and forgot to put a wait function in it? Oh, not everybody's saying yes? Come on. What's that? Fair enough. Well, I've done it repeatedly, and I've seen almost every customer starting out with their products do that. When you do that, you rail your CPU. The faster you run your scan engine, the more load you're putting on your CPU, the less processing resources you have available to actually do something with that data. Under kilohertz, you don't really have a trade-off. You're not really losing anything. Over a kilohertz, you need to take a really hard look at it and see, is it actually worth the trade-off? Obviously, the faster controllers can go a lot faster in terms of scan rates. So, for example, a 9039 quad-core Intel Atom, that thing's awesome. We can run this 10 kilohertz, 15, no problem. Pretty easy. The lowest end compact computers that we've got, ranging in 1 to 5 kilohertz, is when we start raising eyebrows at those. So, again, cheat sheet, it goes in scan engine if it's single point. No waveforms, no arrays, 1 point at a time. Some of our modules do integrate into scan engine via soft motion. Not all of them. Simon, you want to chime in on that one?
Sure. I actually have a session on this on Wednesday, so come listen. But depending on the module, depending on the use of the module as well. Some of it will be FPGA, some of it will be RT side, some of it in the module itself. The module will have.
So short answer, depends on the module. Long answer, come to Simon's session on Wednesday. He'll give you the details.
Very hard.
Oh, come on, that's not that one. But the biggest is pre-written, no FPGA programming required at all. That's usually the main benefit. Typically in system engineering, we recommend, if you're doing single point data anyway, use scan engine. It's free. It's already there, it already works, it's already written. Then for anything where you can't use scan engine, you fall down to the FPGA. Things that force you to go down to the FPGA, any custom triggering logic, custom timing logic. If you're dealing with arrays of data, so waveforms, if you're reading in from an accelerometer module, you're pretty much guaranteed to have to drop down to the FPGA. Single point on a microphone is not particularly useful.
Counting full-meter pulses.
Yep. Yep. And if you're dealing with acquisition rates in the order of hundreds of kilohertz, megahertz, you must be on FPGA. That's the only way you can do it. And it's the classic Spider-Man trade-off. You get great power, but great responsibility, and also you get lots of project risk if you've never done it before. So keep that in mind up front when you're designing your system. If you know you're going to get down to the FPGA and you're not comfortable with it, build in some buffer in terms of your project schedule. Anybody ever click compile on an FPGA project and then see how long it takes? How long does it take?
10 to 15 minutes for most mine.
Your computer is awesome.
There are also fairly small FPGAs that I've had to do as of late.
All right. Yeah, my designs tend to be 45 minutes, an hour. That's not particularly unusual. Typically, we're going to design our systems so that we know up front what needs to go down there. We'll try to keep the logic as simple and modular as we can so we can actually test it on the Windows side without having to compile it for the FPGA. Let's keep that type of thing. And I believe we do have a session on exactly that later in the day.
So remote service compiles also.
Yes, the compile cloud is very handy. Also compile farm if you have stuff that can go on the cloud. That's actually what I use internally. is we set up a compile server in our office that we just dump all of our compile jobs onto. And I actually took out the obligatory XKCD about compiling, but just do a quick search on that one, and it's perfectly relevant here.
303.
What?
It's 303 in case you want to find it.
Wow, Tim. All right, I see my geek credentials to you. Well done. All right, so hybrid mode. If you haven't seen it before, this is what most of my projects end up being, a combination of scan engine and FPGA. Put everything in scan engine that you can because you are strategically lazy. Don't bother wasting your time debugging or testing or building something that already works. Put your modules that can handle scan engine on top, and then anything that needs to be accessed by the FPGA, put it down on the bottom under the FPGA target. You can access both. It's actually surprising to me how few of my customers knew you could do both. We thought it was obvious, but I guess the message didn't get out. So I say it again, you can do both. We've got a couple of ways to move data around in LabVIEW. Kudos to you if you've actually seen everything on this list. And I sincerely doubt that every one of you has experience and knowledge on how to properly use each and every one of these APIs. And if you do, please talk to me because we're hiring. So one of the biggest problems I see, besides not knowing what you want to build in the first place, is once you figure out what data you need to get into your system, it's how to move it around in between the different parts. Take it? Yeah. Come to our session later today about the distributed control and automation framework, and we'll tell you all about it. So if you haven't seen this one before, check your calendars. The sessions for distributed control and automation framework, we're talking a lot about that one. So generally speaking, we get paralysis of choice here. Customer looks at the palettes, they see, holy crap, there's too much here. And generally what I see people doing is they then revert to whichever one they used last time, even if it doesn't make any sense for the project that they're working on. For somebody's first project, that usually means they're using shared variables, global variables, and a poorly designed functional global. That's usually how this turns out. And then about 3 months into that project, they call into NI support, and then we look at it and we get very sad because it's not the right way to move this data around. So to help with that a little bit, we break it into some buckets. These buckets are going to be tags, streams, and messages. You're going to hear this theme repeated a lot, both today and over the upcoming years. We're structuring a lot of our data communication APIs to fall into these paradigms. So if you haven't seen this already, get used to it. Tags, lossy, current value only, single point data. The current temperature is 25°C. Streaming, lossless, high throughput, buffer data. Bringing in vibration data. You care if you have any missing data points there. You need to move a lot of data at once without losing a single bit of it. Messages, reliable delivery, low latency, and usually relatively sparse communication. You're not going to send a lot of messages, but when you do, you want to make sure it gets there and it gets there fast, or at least within a known bounded amount of time. Change the set point. Reset the system. Go. Don't have an emergency stop message, but go is all right. So I'm not going to get into the religious debate as to proper structure of a messaging cluster here. A flexible data type plus something that determines the command. I'm not going to get into the string versus variant debate. Feel free to argue all you like. Come to Lava Barbecue and talk to me about it over a beer. That's fine. I'm not going to get into it. Even with you.
I don't want to get out of
All right. But basically, these are the 3 different types of data typically you can break a system down into. And the right data communication APIs to use for these are different. So, basic cheat sheet. Talking tags. Single point data. Globals and locals, those are single point. This is where a never published shared variable actually can be used. Tag bus, again, if you've never heard of that one, again, come to our sessions later today. We even have a hands-on on how to use a framework we built around that. That can solve a lot of problems for Also, current value table, CVT, that's something that system engineering also puts out. Basically, a big data dictionary that you can access single point data on a lookup basis. We already wrote that. Please don't write your own. Ours is faster. It's already debugged. It works. And it's free. Okay. Network streams, this is when you're trying to move waveform data around between your compact radio and your PC. That's the prime use case of those. That's what it was designed for. TCP, if you don't have LabVIEW on the other end. Queues, FIFOs, etc. I'm not going to go through the laundry list, but this cuts it down pretty significantly. And we can do a little bit better because the available APIs also depend on what's the endpoints of the communication. FPGA to FPGA, FPGA to RT, RT to PC, etc. These are my defaults. If we're just talking about internal to the FPGA, in my personal order of preference for each of the different categories, these are the ones that I use. If you've never seen some of these before, you might want to give them a look. Because you might have not noticed a nice feature hiding in the palette that solves the problem you've been struggling with. Similar. Between FPGA and RT. If you're going to try and move single point data, that goes on the front panel. Please don't ever, 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 ever put an array on your front panel. If you've taken any of our FPGA training courses, you've probably heard that message before. Main reason is it takes up a huge amount of extra resources and buys you absolutely nothing. If you're going with messages, that's when we got the interrupts, and you can use that in conjunction with DMA FIFO. If you're doing streams, DMA. That's the right way to do it. Not the only way to do it. If you're talking about internal to an RT system, we're moving tags around on one system, loop to loop, for example. I usually will use CVT because it's already there, it's already written, it works, it's fast. If I have to, I could use this. Personally, I'm allergic to them. And I'm happy to talk to you about why, but I think I'm going to run out of time to get into that diatribe here. Suffice to say, something that looks exactly like 5 other things on my diagram is not what I want to choose to move data around. I want something that's clear and obvious to me which one it is. That's more of a personal preference than a technical reason, but for me that's pretty compelling. And global variables, yeah, they're on the list, because there's a use case or two for them. For me, I'll only accept a global variable in my systems if it's a write once, read many type of scenario. If you got multiple writers to a global, you have just failed a code review with me. Congratulations. Don't do it. It seems so easy. It's like swiping that credit card when you can't pay for it. It's so easy. It's so easy. I want that thing from Amazon. No, just don't. It's not worth it. And if you're dealing with streams, start with RT FIFO. If you never used the RT FIFOs on our compact radios and you're moving waveforms around, you really should take a look at it, because they can save you some of the memory allocation and processor overhead headaches if you're dealing with queues. They put a few more restrictions on you, but those restrictions are there to help you, not to hurt you. We promise. Okay. And if we're talking about network, this is usually where things get fun. Once you introduce an Ethernet cable into the equation, you get a whole host of new variables into your system. This is, by the way, the only use case where I will let somebody use a network published shared variable on a system that I'm reviewing. If you're moving single point data between compact radio and a PC, that's what they're for. If you have a shared variable of type array or type waveform, you have made me sad. It's not a good idea. And if you have a shared variable named emergency stop, just stop now. Just get out. You're doing it wrong. Messages, network streams. These are very, very good for both streams and messages because they've got reliable delivery, and they'll also reconnect. Have you ever written a TCP daemon for your systems, the loop that handles TCP connection? And how many times have you realized you forgot about error 56? A couple of nods and shamefaced faces, yeah. And then if you have to do reconnection, you need another loop to check the connection status, or reconnect if someone plugs the cable back in. Yeah, we wrote that loop. It's part of network streams. It's already there. Just use it. You can pull the cable and connect it again. The main restriction with network streams is they only work LabVIEW to LabVIEW. So if you're talking LabVIEw to JavaScript, it ain't going to work. If you're talking LabVIEw to .NET, you could find a way to make it work, but it's going to be a little janky. And those are the cases where I have to fall back to usually a custom TCP protocol. Have you written those custom TCP protocols? Yeah. Yeah, System Engineering publishes one that does a really good job, and it's already written and debugged. You might want to use this one if you haven't seen it before. Simple TCP messaging, STM, talk about that in section 430. So if you've ever written a custom TCP protocol and got annoyed that you forgot to handle an error, give this a look. Streams, they might do. Not going to belabor that point given the amount of time we have. All right. So the different modules or loops or things that go into my system. I list the top two outside of the big red box because everybody thinks about acquisition and telling your system what to do. People tend to forget about the other parts, and those are in every one of the systems that I make. So I saw some hands go up about watchdogs, and it's good. How many of you handle all of your errors? How many of you looked at your project and thought, man, when I get some free time, I should really put better error handling in here? Yeah. When does free time happen? Yeah, no. You got to put it in there. I mean, at least try. I mean, I've seen a lot of systems where the error handling in the system consists of wiring the error cluster to the edge of a sequence just so it won't automatically pop up an error when one happens. Come on. What? Ooh, I see some knowing nods. Okay. Don't do that. And also, if you're dealing with a compact RIO system running deployed, any of you ever have an error after you deploy a system? Something goes wrong? How do you know what went wrong? You put good trace logs in your system beforehand to log all the interesting things your system's been doing, right? If you haven't, and you start seeing a system fail in the field and your customer asks you what happened, and your answer is, I don't know, let's put in some logging code and wait a week for it to reproduce. You don't have a happy customer. Put in those logging hooks at the beginning, sprinkle them throughout your code, and then when your customer tells you something weird happened or the system isn't responding, all you have to do is tell them, send me the log file, and I can take a look. We've got some libraries to help with that as well.
Are those libraries you have to download, or they are in the software?
Libraries you have to download, and I'll give a plug here, I'll repeat at the end, ni.com/reference designs. That's where System Engineering publishes all of the reuse code that we make.
Reference design?
One word. ni.com/reference designs. There'll be a link shown on the last slide.
Okay.
They're all on the tools network as well, so you just download from there.
Yep. We post pretty much everything on VA Package Manager. We post some that are still kind of in work or not ready for prime time just on that page. Either way, we like to point people to ni.com/reference designs because that's where the documentation is also. All right, so errors. You'll find this familiar. This is my typical error management strategy. First, every single loop in your system should at least attempt to handle or ignore its own errors. At least try. At the very minimum, it should be reporting what every error that it sees has been. And if it needs to be taken care of by some higher level handler, tell it to another loop. Typically in my systems, I've got one loop whose sole responsibility is to listen for errors from all my other loops. It then gets to make a decision of, is this error so important that I need to go into a safe state and reboot? Or can I just continue on with my life after logging into my good trace logs that I already had built into my system? So we've got some of this in our sample projects. We've got one reference design structured error handler that can help. And also, again, you'll hear this repeatedly throughout the day. Tag bus, which is used in the distributed control and automation framework, already has good error handling, error management built in. So it might look something like this, where each of my loops has specific handling logic at the end of it to determine, say, for my TCP loop, do I think error 56 is something that requires a shutdown of the system? Timeout error? Probably not. I can probably just ignore that one or log it to disk instead of saying, throw my hands up and reboot the system. If my acquisition logic can't talk to my C-series modules anymore, that's probably a critical error that needs to get a resettable system. Depending on what your application is, individual error codes will have different meanings, different severities, That's why you need to put some specific handling logic on each of your loops and have something to manage the actions if you do see a critical error. In our sample projects, which this is one of them, the error management logic is actually in here. A little bit hard to see, but it's got cases for when critical errors are reported in here. Personally, I tend to break it out into its own loop. Sample projects, put it into the main message handling loop. Do whatever works for you. Just try, please. All right. System health. Has anybody ever had a memory leak? Yeah. How do you tell that you have a memory leak?
Look at memory.
You run out of memory. Yeah? Yeah, that's one way. Yeah. What happens when you run out of memory? Yeah, bad things happen. If your system can't allocate any more memory, bye-bye program. Generally speaking, you want to know about that before it happens. You want to do some testing up front to determine, wow, my memory's going up. If I keep this running for another week, it's going to reset itself. You might want to find that out before your critical control system stops responding and all the outputs get locked in their current state. That would be bad if the valves stay open when they're not supposed to. Every one of my systems has a system health loop that monitors CPU, memory, and disk usage. Remember those nice trace logging files that we talked about? They're not so nice if they fill up your drive and you've got no more space to log your actual data. Be monitoring that. Have some simple logic in there to delete old files if the disk gets too full. You can steal code from our sample projects. There's a sub-VI in there that does exactly that. You can just say yoink, put it into your code. I do it every time. And you know the LEDs on the front of your compact Rio? They're really useful. Blink them. Tell your users what's going on. If your system has hit a critical error, turn the light orange. Or blink it orange, or whatever. Give it some visual indication that A, it's running, or B, it self-detected a problem. It takes maybe 15 minutes to write some LED logic, but it's saved me a lot of trouble when doing some field debugging. Even just to tell that my system is still functioning. It's still blinking, all right, it's alive. Yeah.
Have you done anything better in the Linux RT systems with memory usage reporting?
Ah, yes. So on the Linux RT systems, if you look at free physical memory, the property that gets reported out is wrong. Specifically, if you are writing files to disk, it charges any memory allocated to the write-to-disk buffers against the application. The correct way of saying what it's reporting is it's reporting memory that has never been allocated ever. Pristine, clean memory that's never been given to anyone. That doesn't mean that memory is unavailable to be given to LabVIEW. Once it's been given to a file I/O buffer, it doesn't show up in that list. And if you're doing a stream-to-disk application on a Linux RT target, you'll actually see the memory usage go down continuously, hit 0, and keep running. Because what's being reported in that property is incorrect. We have a knowledge base article published on NI.com that shows the more correct way of doing it through some system calls, and we're working on rolling that into the product as well.
Yeah, because that's what we ended up having.
Yeah. So if you haven't run into that before, it's fairly common for us to hear a panicked phone call from someone who has done their job right. They're monitoring the memory usage, they're testing their deployed system, and they see something scary. We put the bug in your ear that if you're doing a continuous writing to disk type of application, you will see that reported memory drop. Don't get scared until you read that KV. Look at other ways of reporting memory. Test that. If that one is flat, you're fine. We know about it. We're working on it. The primary reason why it's that way is the same API had to be used for both the VxWorks targets and the Linux targets. VxWorks targets have a flat memory system. Linux is much more sophisticated, so the reporting has to be a lot more complex. Good question. Yeah.
I would come with the disk usage. I had a customer actually fill up their hard drive, and because then therefore the program would not come back up. Linux RT will go into safe mode if it boots a full hard drive.
Yes. And that's there to protect you. The OS needs to be able to talk to the disk.
So keep it clean.
Yeah, it's code that's already written. You can steal it from the sample projects to check disk usage. There are examples on NI.com how to get the correct memory usage as well. Trace logging. Log some data to disk. Usually each of my loops, when I go into a state change, for example, I'm going to log it. Every time I receive a message from a user interface, I log it. I log it with a timestamp. Otherwise, those logs are not particularly useful. I also set all of my loops to log into one file so that I can actually do comparisons between them. I've got one trace logging loop in my system that receives messages from every other loop in the system that hits the disk. And have you noticed the resolution on our timestamps? What is it? What? Yeah, it's milliseconds typically. Well, we could run a lot faster than a millisecond in terms of number of operations going on. If everything, it's 10 different operations have the same timestamp, and they're each logging to independent files, you have no idea which one happened first. Send them all into one bottleneck, then you can get a sequential log. Much more useful. And if you're considering doing this, look at syslog. If you've ever wondered why isn't there some already pre-written standard for reporting messages, well, there is. It's been around for decades. It's called syslog. We support it on our targets. There is a syslog daemon already running on your compact RIO. Use it. Come to my session at 4:30 and I'll tell you how. All right. Watchdogs. Simple logic. If you have a compact RIO deployed on a wind turbine in the North Sea, you probably don't want to go out there and press the reset button if something goes wrong. If, heaven forbid, you forgot to test your code thoroughly, or there's a bug left, or some bad state happens, this is your safety net. This is your get out of jail free card. Our compact RIO targets have hardware timers on them that you can use to reset the system if it stops responding. It takes only a few minutes to figure out that weird cluster and how it works. Promise it's worth your time. Set your system to reset if it hasn't been, if the watchdog loop hasn't executed after some period of time. Usually I set mine for after 5 minutes of inactivity of the system not responding, reboot the whole system from scratch. Try to recover yourself. And of course, before I do the reboot, I put a message into my trace log to say what happened. Okay. So there's the ridiculous cluster. This is the only one that really matters. Don't worry about these. They don't really matter for compact RIO system. We've used the same API for our targets for, I think, 15 years now. This is the one that you want. And you have to whack is the term. Sometimes we say pet the watchdog. You have to whack it once to start the timer. So if you forget to whack it once and you're wondering why it doesn't reset, it's because you didn't actually turn it on. And one of the things you can also do is to set your FPGA code to be waiting for a signal coming in from your RT system to see if the RT side has failed to respond. This will let you put your I/O into a safe state before you reboot. So you might want to close those valves, turn off the power to your systems before you go into an uncontrolled state. Otherwise, it detonates. Configuration. If you have constants all over your diagram, you're doing it wrong, pull it out into a file. We've got tools for this. Come to the Distributed Control Automation Framework sessions. I'll show you how. Come to the session at 4:30. I'll show you some other tools. There are sample projects. I don't usually use them as a straight starting point for an application, but I do use them as a crib sheet. There's some nice code in there, like the disk management, how much free space you have available on the disk, and removal of files logic. You can just straight up copy and paste. It also shows you a correctly designed, but designed by committee, implementation of a compact RIO system. It's worth at least looking at. And this is basically what it ends up looking like. This is one of the projects that we post out on the Tools Network and on VI Package Manager. If you are doing waveform acquisition on compact RIO, there's a lot of code that you don't have to write because we already wrote it for you and we posted it. It will cover about 80% of the logic necessary to pull in data from accelerometer or microphones, get it in a nice waveform with correct timestamps, and also does all the error handling. Because you do great error handling on your FPGA code, right? Yeah, we did. Steal it. All right. And I've got about 2 minutes left on here. If you're going to be doing any project of any size in LabVIEW, you should be using source control. How many of you use source control today? Not every person raised their hand. Okay. So, what? Yeah, so zip files, if you can't read it in the back, this is LabVIEW project.zip, LabVIEW project copy.zip, LabVIEW project copy final.zip, copy final v2, copy final v2 fix bug.zip. Have you ever seen source control like this? Yeah. That's not source control. That's just pain waiting to be experienced. And I give you a nice chart. If you need to make a decision about source control, this can help you decide. So, yeah, we never make mistakes. That's why I added the second box. Does anybody work with make mistakes? Probably. Okay. So, as promised, some links. If you want to see what kind of reference designs that we have published from System Engineering, come to my session at 4:30, or go to ni.com/reference designs. If you want to see recommendations distilled from a lot of customer interactions in a very, very long format, see the Compact Grid Developer's Guide. There's some good nuggets in there. And if you want to take a look at what you can download to do some of your work for you, LabVIEW Tools Network and VI Package Manager is where you'll find that. So, I should be able to take a question or two before we switch over to the other session. We did end a few minutes late, but no more minutes late than we started late. So. On source control. Yep. Single computer with no network capabilities, what do you use? Frankly, it tends to come down to what are you comfortable with using. So there's lots of free tools available. Personally, on my computer, I've got about 6 of them, because it usually depends on what source control tool my customer uses. And that's usually what it comes down to for me. Whichever one you want, frankly. We work with Git, Perforce, SVN, especially with Force install. Viewpoint's got some nice tools on VI Package Manager you can download to help with some of that. What's that? They don't have to be network published, and you can use them locally just as well. Frankly, I say it doesn't matter which one you choose, just use one. Whichever one is comfortable to you. Using an incorrect source control tool is still better than not doing source control. Yes?
Where will your slides be?
Where will my slides be? The canned answer is where all the other NIWeek slides are going to be, and I don't know exactly where that is. All right, if there's any other questions, come chat with me so I can let the next presenter set up. Thanks for your time.